Girls, so starting with the first question on that relative velocity 2 document, the closest distance document, it says the following table shows the movement of two vehicles, P and Q. Now they're either moving towards or away from a junction, depending on which scenario we're talking about. So in this particular case, you've got vehicle P. It's moving with a velocity of 5 meters per second in an easterly direction, and its position is 100 meters west of this right-angle junction. So here's my right-angle junction. I'm going to put in P's position. So it's 100 meters west. So the origin, the west will be over here relative to the origin. So it's 100 meters west of the origin. This is P's position. Okay, Q is travelling 12 meters per second in a northerly direction, and its position is 300 meters south of the junction. Okay, so south of the junction is down here. It's 300 meters south, so I'll just put that in here. And this is where Q is. Now these two cars, it tells me the speed they're moving at. So velocity of P is 5 meters per second east, which means it's moving in this direction. It's going in that direction towards the crossroads. And Q, so I'll put VP is equal to 5, and the Q is 12 meters per second north, so it's travelling up the y-axis like that. So the VQ is equal to 12. Alright, so that's the first part. The question says, that's the situation. Draw a diagram to show the positions. So that's the first part. The second part says, how long does it take P to reach the junction? So P is 100 meters from the junction. It's travelling with a speed of 5. So how long does it take P to reach that junction? So of course, remember, speed is equal to distance over time. Time will be equal to distance, which is 100, over the speed, which in this case is 5. So it takes it 20 seconds to get to the junction. That's part 1 is the diagram. Part 2 is how long it takes P to get to the junction. Part 3 says, where is Q when P is at the junction? Okay, so in 20 seconds, Q is here initially, it's 300 meters from the junction. How far has it gone in 20 seconds? Right, so it was 300 meters from the junction. It has now travelled the distance of speed by time. So I'm going to subtract its speed, which is 12, multiplied by 20, which is the time. So that means I'm going to take 240 from 300, and I get that Q is now 60 meters from the junction. Okay. Now the fourth part of the question says, find the closest distance they can be to each other. So these two vehicles, the closest that they can be. So in this instance, what you do is you redraw your diagram, and one of them, when you're redrawing, one of the vehicles should be at the origin. So one is at the origin, and then you see where the other one is relative to it, and then position the other one. Position the second one. Okay, so redraw your diagram. Off we go. We're going to redraw this. We know that P is actually at the origin because we've already done that, how long it took P to get to the junction. So we'll put P here at the junction. Now where is Q relative to P? Well, it's 60 meters from the junction, so we'll put Q down here. Now then, in order to get the closest that they are to each other, you're going to put in the relative velocity into that diagram. So you redraw the diagram, you position one at the junction or the origin, then you position the second one. The third thing you have to do is to find the relative velocity. Okay, so I'm going to find the VPQ. Now, in order to do that, I need to know what VP is and what VQ is, because we know from the last lesson that VPQ is VP minus VQ. Okay, so what's the velocity of P? The velocity of P, I'm told, is 5 meters per second in an easterly direction. So that means it's moving in a positive I direction. So it's 5I plus 0j. I'm going to turn everything into the I and j components. What's the velocity of Q? The velocity of Q is travelling north at a speed of 12, so that means 0I plus 12J. And then when you do a VPQ on that, it becomes 5I plus 0J minus 0I plus 12J. Put that in brackets and watch your signs. So this will become 5I minus 12J. Now, whether you're asked or not, if you ever find a relative velocity, you immediately, two things you immediately do is you find its magnitude and its direction. So you do that even if you're not asked to do it in the question. So the VPQ here, its magnitude is going to be the square root of the I component squared plus the j component squared. And of course when I work that out I get 13. The direction of this vector, so 5I minus 12j, look at it. It's going 5 in the positive direction, minus 12 in the j direction. So really, that vector is this kind of direction. That's what it is. So this is the VPQ. That's the direction of the VPQ vector. And this angle here, I'm going to call it alpha. The angle that it makes with the positive sense of the I-axis gives me its direction. So the tan of alpha is equal to, now remember it's gone out 5 units along the I-axis and it's 12 down in the j direction. So the tan of alpha is going to be 12 over 5, opposite over adjacent. Okay, now let's work this out then. So what is, I'll just get my calculator, what is the tan of 12 over 5? So the second function tan of 12 divided by 5 is 67.38 degrees. So alpha is equal to 67.38 degrees. So again, whether you're asked for it or not, you always get this, the magnitude, the speed, and you always find this direction. Okay, now we've got all the information now in place. Now we have to find the closest distance that they can be to each other. So in order to do that, you must put the relative velocity line onto your diagram. So I'll do that in green. So here's my diagram, VPQ. P is at the junction. VPQ is the relative velocity line. I'm going to put that on here. And look at its direction. Now I know all about it. So it's travelling like this. So I'm going to put it in like this. That's it. That's my VPQ vector, or my VPQ line. Okay. Now, question asks me then, find the closest distance. Once you've done that, once you've put the line in, you drop a perpendicular from Q's position down onto that red line. And that distance there, I'm going to call it D. D is the closest distance. D is known as the closest distance. You've got to find D. So if you look at that diagram, what you actually have is a right angle triangle, because I've dropped a perpendicular, so that's a right angle here. What do we know? We know the distance that Q is from the intersection. We've already found that. It's 60 metres from the intersection, so that's 60. This, of course, is the hypotenuse in that triangle. So here's your right angle. That's the opposite side, the hypotenuse. And I'm looking for D. So I'm missing an angle. But I do know that this red line makes an angle alpha with the positive sense of the I-axis. So I have that alpha there. And I know it's 67.38. And of course, if I take that from 90, that will give me this angle here, there. So that angle dot I'll call it, is 22.62 to the nearest degree. So now using that right angle triangle, I can say that D, the closest distance, right, so the sine of that dot is equal to D over 60. So D is 60 times the sine of 22.62. And when I work that out, I'll multiply that now. If I get the sine of that angle, 22.62, multiply it by 60, I get 23 metres. So my closest distance is 23 metres. Okay, so that's the first one. Now the last bit of that question is part 5, which says, how long does it take for this closest distance to occur? So the distance, or the time it takes for this to happen. Going back up here to my time is equal to distance over speed. So the time for this to happen, in this case, is the relative distance divided by the relative speed. The relative distance divided by the relative speed. So that means all my information must come from the red line, because that's the relative line. So the time for this to happen then is, now the relative distance will be the distance on the red line. So if we look at this triangle here, that is 60, the hypotenuse is 60. I now know that D is 23 meters. So using this little right angle here, I can find this angle over there using Pythagoras. So 60 squared minus 23 squared, and getting the square root of that, that gives me 55.42. So the distance, the relative distance, is 55.42. So I've taken this now from this triangle again, the relative distance, and I'm going to divide it by the relative speed, which is the magnitude of the VPQ line. And of course the magnitude I already know is 13. So that means if I divide that by 13, that's going to give me 4.26 seconds. So the time for this to happen, 4.26 seconds, is when they are at their closest from after P reaches the junction. So it took 20 seconds for P to reach the junction, and then it took another 4.26 seconds for them to be the closest they could to each other.